In the sprawling, chaotic lineage of computer science, there are certain laboratories that function less like academic departments and more like crucibles where the future is forged in high heat. The University of California at Berkeley in the 1970s and 80s was one such place. It was a chaotic environment, cluttered with Digital Equipment Corporation VAX workstations, the air heavy with the smell of ozone and the dust of chalkboards covered in mathematical proofs. This was the birthplace of the Berkeley Software Distribution, or BSD, a version of Unix that would eventually breathe life into everything from modern servers to the iPhone. Yet, in the shadow of the operating system wars, another revolution was quietly taking shape, one concerned not with how computers ran, but with how they remembered. This narrative begins with Michael Stonebraker, a computer scientist possessed by a relentless, quiet intensity. He had already helped define the relational database with a project called Ingress, but by the mid-80s, he saw the cracks in his own creation. The rigid rows and columns of the time were too stifling for the complex, unstructured data that was beginning to emerge. He envisioned a system that could understand objects, geometry, and arrays. A system that treated data not as dead inventory but as living, evolving concepts. He called this project Postgres, a name that signified simply that it came after Ingress. It was a declaration of evolution, a tool designed to break the conservative mold of information storage. At its core, PostgreSQL, as it is known today, is an object relational database management system. It is a piece of software that resides on a server, acting as the gatekeeper and librarian for vast reservoirs of information. When an application needs to remember a user's profile, a financial transaction, or the precise geographic coordinates of a shipping container, it hands that data to PostgreSQL. The database writes it to the physical disk, indexes it for rapid retrieval, and ensures that it remains consistent even if the power fails or the hardware melts. It is used by entities as diverse as the Federal Aviation Administration to track flights, by Apple to manage vast ecosystems of user data, and by Instagram to handle the relentless torrent of social interactions. However, to understand its power, one must look past its utility and see it as a triumph of philosophy. It represents the belief that data integrity, the absolute truth of the record, is more important than raw speed or marketing hype. This philosophy was not easily won. It was forged in a fire of neglect and near extinction. When Michael Stonebraker left Berkeley in the early 1990s to pursue commercial ventures, the Postgres project faced a crisis common to academic software. The original research grant, provided by the Defense Advanced Research Projects Agency and the National Science Foundation, had served its purpose. The goals were met. The papers were published. In the brutal economics of academia, the project was effectively dead. The code, a complex beast written in the C programming language, was left to gather digital dust. It was powerful but eccentric. It used a query language called PostgIS, a syntax that was mathematically elegant but practically useless to a business world that had already standardized on SQL, the structured query language. By 1993, Postgres was an abandoned artifact, a piece of brilliant machinery with no operator and no fuel. It should have remained a footnote in computer science history, a prototype discussed only by graying professors. But the nature of open-source software is that it allows for resurrection. 2 graduate students at Berkeley, Andrew Yu and Jolly Chen, refused to let the system die. They looked at the sprawling code base and realized that its object-oriented architecture was decades ahead of its time, but its language was its prison. In a labor of tedious, unglamorous engineering, they stripped out the PostgIS language and replaced it with a SQL parser. They renamed the system Postgres 9.5. This was the pivotal moment, the turning point where a research experiment was transmuted into a viable tool. When they released it to the internet, they did not sell it. They gave it away under a permissive license, allowing anyone to use, modify, or sell it without paying a cent to Berkeley. This decision, seemingly minor, planted the seeds for a global empire. It removed the friction of adoption. Slowly, a team of volunteers from around the world began to coalesce around the code. They were not employees of a single corporation, but a collective of pragmatists from Canada, Russia, Japan, and Europe. In 1996, they renamed it PostgreSQL to honor its heritage while acknowledging its new SQL capability. They were the scavengers who found a diamond in the rubble, polished it, and built a cathedral around it. The impact of this resurrection is difficult to overstate. Prior to PostgreSQL's rise, the database market was a feudal system dominated by giants like Oracle, IBM, and Microsoft. These corporations charged exorbitant licensing fees, often hundreds of thousands of dollars per processor, for the privilege of storing data reliably. They held their customers hostage with vendor lock-in, creating a legal and financial stranglehold that stifled innovation for small startups and public institutions. PostgreSQL introduced a new variable to this equation: liberty. It offered an enterprise-class database for free. This did not just save money, it democratized the ability to build complex systems. A student in a dorm room in Mumbai could now wield the same data processing power as a bank in Zurich. Over the decades, this shift transferred billions of dollars in value from software licensing fees into actual innovation. Companies like Skype and Reddit were built on PostgreSQL because they could scale their infrastructure without bleeding capital to Oracle. The economic liberation provided by PostgreSQL is one of the silent engines of the modern internet economy. However, the path was not without controversy. The database wars of the 1990s and 2000s were fought with lawyers and marketing budgets. Oracle, led by the aggressive Larry Ellison, frequently dismissed open-source databases as toys, lacking the sophisticated features required for serious business. There was a prevailing narrative, fueled by corporate fear, that open-source software was legally dangerous, potentially infringing on patents or lacking the indemnification that a contract provided. This fear was a weapon used to keep chief information officers in line. Furthermore, PostgreSQL was often criticized for being slower than its lighter, less rigorous cousin, MySQL. While MySQL prioritized speed by cutting corners on data correctness, PostgreSQL refused to compromise. This led to a years-long technical and political debate within the developer community. Was it better to be fast and loose, or slow and correct? PostgreSQL chose correctness. For years, this cost them market share. They were the tortoise in a race obsessed with hares. But as applications grew more complex, and as data became the lifeblood of the global economy, the cracks in the faster systems began to show. Data corruption in financial systems is not an inconvenience. It is a catastrophe. Slowly, the industry began to swing back toward the rigorous engineering that PostgreSQL had championed all along. The mechanism of this rigor is a study in the psychology of machines. At the heart of PostgreSQL lies a concept known as write-ahead logging. To understand this, one must view the database as a paranoid entity, deeply aware of the fragility of existence. It assumes that at any moment, the power will fail, the operating system will crash, or the hardware will seize. Therefore, before it makes any change to the actual data files, before it updates a bank balance or records a vote, it writes its intention to a separate journal, the write-ahead log. This is a sequential diary of everything the database plans to do. Only after the entry is safely on the disk does the database proceed with the action. If the system crashes mid-operation, it reboots, reads the diary, and replays the events exactly as they were intended. This is a profound architectural decision. It externalizes risk. It acknowledges that chaos is inevitable, and that the only defense is a meticulous record of the past. It is a digital manifestation of integrity, saying what you will do, writing it down, and then doing it. This obsession with consistency extends to how PostgreSQL handles time and perception. In a massive system, thousands of users are reading and writing simultaneously. A naive system would lock the data every time someone tried to change it, forcing everyone else to wait. This creates a bottleneck, a traffic jam of information. PostgreSQL solves this with multi-version concurrency control. Instead of overwriting data, the database creates a new version of the row for every update. If a user is reading a table while another user is updating it, the reader sees the old version, the ghost of the data as it existed when their query began. The writer creates a new future. They exist in parallel timelines, oblivious to one another's conflicts. The database manages these layers of reality, serving the correct truth to each observer. This allows for immense scalability, but it comes with a cost. The system becomes cluttered with dead rows, the debris of past transactions. To handle this, PostgreSQL employs a process called vacuum. Like a silent janitor, the vacuum process moves through the storage in the background, identifying the versions of reality that are no longer visible to any active user and reclaiming the space. It is a cycle of death and renewal, a biological rhythm inside the silicon. The architecture of PostgreSQL is not merely about storage, it is about extensibility. Michael Stonebraker's original vision was to create a system that could be taught new tricks. This is realized through its index access methods. In most databases, an index is a simple lookup tool, like the index at the back of a book. In PostgreSQL, indexes are sophisticated data structures that can be swapped and customized. The B-tree is the standard workhorse, the reliable librarian that handles sorting and equality. But for more complex data, PostgreSQL offers the generalized search tree, or GIST. GIST is an infrastructure for building new access methods. It allows the database to understand concepts like overlap or contains in geometric shapes. Then there is the Generalized Inverted Index, or GIN, which acts as a document archivist, perfect for dissecting and searching full-text documents or complex arrays. Block Range Indexes, or BRIN, act as wilderness scouts, summarizing vast ranges of data on disk to allow the database to skip over huge sections that are irrelevant. These are not just features. They are distinct personalities within the code. Specialized agents that allow PostgreSQL to adapt to workloads that its creators never imagined. This adaptability saved PostgreSQL during the great data upheaval of the 2010s. This was the era of the NoSQL revolution. Developers, frustrated by the rigid schemas of relational databases, flocked to new systems like MongoDB, which stored data in flexible, JSON-like documents. These systems promised speed and agility, arguing that the relational model was a dinosaur. For a moment, it seemed as though the era of SQL was ending. But PostgreSQL did something unexpected. It did not stubbornly cling to the past, nor did it abandon its principles. It assimilated the threat. The community introduced a data type called JSONB. This allowed users to store unstructured nesting documents directly inside the strict relational environment. Unlike the NoSQL competitors, however, PostgreSQL allowed users to enforce rules on this chaotic data and join it with structured tables. It was a masterstroke of strategy. It offered the flexibility of the new world with the transactional safety of the old. Companies that had fled to NoSQL databases often found themselves returning to PostgreSQL once they realized that data without structure eventually becomes a swamp. JSONB prevented a mass fragmentation of the industry, keeping vast swathes of the tech sector united under a single, reliable banner. Perhaps the most tangible impact of PostgreSQL's extensibility is found in the physical world. In the early 2000s, a Canadian consulting company called Refractions Research, led by Paul Ramsey, began working on a problem involving digital mapping. They needed a database that could understand geography, not just text names of cities, but the actual mathematical shapes of coastlines, roads, and property lines. They built an extension for PostgreSQL called PostGIS. This transformed the database into the world's most powerful engine for spatial reasoning. Today, PostGIS is the standard for geographic information systems. When a ride-sharing app calculates the nearest driver, or when a disaster response team models the floodplain of a hurricane, they are often querying a PostgreSQL database. It powers OpenStreetMap, the collaborative project that maps the entire world. It is used by urban planners to redesign traffic flows and by epidemiologists to track the spread of viruses. This is where the code touches the pavement. PostgreSQL has quietly become the spatial cortex of the planet, the underlying grid upon which we understand our physical reality. The triumph of PostgreSQL is best viewed through the lens of its former enemies. By the late 2010s, the major cloud providers, Amazon, Google, and Microsoft, stopped trying to convince the world to use their proprietary database engines. Instead, they capitulated. Amazon launched Aurora, a high-performance database service that is fully compatible with PostgreSQL. Google Cloud SQL and Microsoft Azure followed suit, offering managed PostgreSQL services as flagship products. These trillion-dollar corporations realized that they could not compete with the collective momentum of the open-source community. They could not out-engineer a global network of volunteers who were driven by passion rather than quarterly profits. This is a rare phenomenon in capitalism. It is akin to a public library forcing Barnes & Noble to start lending books for free. PostgreSQL became the Linux of databases, the default standard that serves as the bedrock for the industry. This dominance has shifted the balance of power in the war against Oracle. For decades, Oracle was the default choice for the Fortune 500. But the combination of Oracle's aggressive auditing practices, where they would investigate customers to extract more fees, and the maturing of PostgreSQL created a migration exodus, known as re-platforming. This movement saw massive entities moving their core transactional systems to PostgreSQL. The Federal Aviation Administration, tasked with the safety of millions of passengers, utilizes PostgreSQL. The French Family Allowance Fund, managing payments for millions of citizens, migrated to it. Even in the financial sector, where conservatism is a religion, banks began to adopt PostgreSQL for trading platforms and risk analysis. This was not just a technical migration, it was a declaration of independence. It was organizations reclaiming sovereignty over their own data, refusing to rent their infrastructure from a landlord who kept raising the rent. Yet, beyond the money and the corporate wars, there is a deeper philosophical resonance to PostgreSQL. In a digital age characterized by move fast and break things, PostgreSQL stands as a monument to the opposite virtue. Move slowly and preserve truth. The development community is notorious for its caution. A new feature might be debated for years on the mailing lists before it is merged. Patches are scrutinized with a level of rigor that borders on the obsessive. This culture is the immune system of the project. It rejects the hype cycles that plague the technology industry. When blockchain was the buzzword, PostgreSQL ignored it. When artificial intelligence began to dominate the headlines, PostgreSQL added vector support quietly and methodically, without rebranding itself as an AI database. This stoicism creates trust. Scientists shielding climate data, archivists preserving history, and governments recording census data choose PostgreSQL because it is built to last. It is designed with a time frame of decades, not fiscal quarters. The governance of the project reflects this stability. Unlike many open-source projects that are effectively controlled by a single company, PostgreSQL has no owner. There is no PostgreSQL corporation. The trademark is held by a non-profit foundation. The core team is composed of individuals employed by various competing companies: Enterprise DB, Microsoft, Crunchy Data, and others. This creates a balance of power, a system of checks and balances that prevents any single entity from hijacking the roadmap for their own profit. If one company tries to push a feature that benefits them but hurts the community, the others block it. It is a model of digital democracy that has survived for over 30 years. It proves that disparate groups, often competitors, can collaborate on a shared infrastructure that benefits the collective. The global impact of this technology extends to the developing world. In nations where software licensing fees can be a prohibitive barrier to modernization, PostgreSQL offers a way forward. Governments in South America and Southeast Asia have adopted policies preferring open-source software, largely to reduce dependency on foreign corporations. PostgreSQL enables a hospital in rural Kenya to run a sophisticated patient record system on commodity hardware. It allows a fintech startup in Indonesia to process payments with the same reliability as a Wall Street bank. It levels the playing field, ensuring that the tools of the digital age are not the exclusive property of the wealthy. It is a tool of empowerment, a lever that allows small teams to move heavy mountains of data. Consider the metaphor of the elephant, the logo of PostgreSQL, named Slonik. It is fitting. An elephant is large, strong, and intelligent. It is not the fastest animal on the savannah, but it is unstoppable. It has a long memory. PostgreSQL is the elephant of the digital world. It remembers every transaction. It carries the weight of the world's information on its back. While the technological landscape around it shifts like sand, with frameworks rising and falling, languages coming into and going out of fashion, PostgreSQL remains. It continues to add features, partitioning for massive datasets, logical replication for distributing data across the globe, just-in-time compilation for complex queries, but it does so with a calm, deliberate pace. The story of PostgreSQL is, in the end, a story about the victory of the long game. It is a rebuke to the culture of instant gratification. It teaches us that the most important systems are not the ones that dazzle us with flash, but the ones that disappear into the background because they work so perfectly. It shows that a group of people, connected only by the internet and a shared belief in code quality, can build something that outlasts and outperforms the products of the world's richest monopolies. It is a reminder that in the architecture of the future, the foundation must be solid. PostgreSQL is that foundation. It is the concrete and steel of the internet, the silent keeper of the ledger, the unblinking eye that watches over the data of civilization. As we move further into an era of artificial intelligence and automated decision-making, the importance of a reliable, transparent, and truthful record of reality becomes paramount. PostgreSQL provides that record. It started in a cluttered room in Berkeley, survived the valley of death, adapted to a changing world, and emerged as the guardian of the world's digital memory. It is a testament to the enduring power of serious, quiet engineering.